I am able to produce extremely homogeneous and equal cellulose filaments on a business scale.
Words written to an English business associate by Gerard Philips on November the 14th, 1890. Based on this skill, the Philips factory for light bulbs was founded in 1891. Within a few years, the company went through an overwhelming growth due to the powerful influence of Gerard's younger brother, Anton. By 1900, Philips light bulbs were being sold all over the world. In 1908, Philips, with its 1,000 workers, was the largest employer in the Netherlands. Thanks to their own glass factory, Philips was able to produce 30 million light bulbs a year by 1917. Back in 1914, a start was made with what was to become one of the world's largest research centers, the Philips Natuurkundig Laboratorium. Philips realized that their own basic research was absolutely necessary for the company's survival, growth, and development. Thanks to the fundamental research in these laboratories, Philips started producing an ever wider range of products and began its growth into one of the world's leading electronics companies. Today, Philips' activities cover a huge variety of technologically advanced products in the fields of medical systems, lighting, electronics components, consumer electronics, and communications and data systems. The now global company, once dependent on the one single product, the light bulb, now has to cope with one other single important product again, the integrated circuit, known as the chip. Not only in highly advanced technical environments, but also in everyday life, ICs have become a regularly used tool. Chips today are a critically important product for the electronics industry. In the near future, there will surely be an increasing need for integrated circuits.
Stop and insert the appropriate disc.
Within a few years, 20% of a car's total cost will be spent on electronics.
Take turning left at the end of the street. Take second exit at roundabout.
Existing systems will be upgraded by the application of newly developed integrated circuits. As chips will inevitably shape the future of electronics companies, Philips knows that designing and producing their own chips is of vital importance. The production of integrated circuits demands extremely specialized know-how and experience. Philips has earned these by manufacturing integrated circuits for years. In order to meet market needs, new chips have to be regularly designed, another Philips skill. Whereas integrated circuits are growing more complex and are designed with ever more components in less space, completely new design and production technologies have to be developed. That is why in 1986, Philips made a major investment in a comprehensive new IC Research and Development Center on the site of the Philips Research Laboratories in Eindhoven. One of the two buildings houses office facilities and the IC designers with their modern computer systems. This building is directly connected to the technology building. Several support installations are close by. On the ground floor of the technology building, service rooms can be entered from the outside for the supply of gases and chemicals. Via complex piping networks, the necessary chemicals and other required materials are transported to the clean room, which is situated directly above this level. From the top floor, supply of fresh air is regulated. One level lower, the air treatment units of the cleanroom tunnels are located. By giving each operation tunnel in the cleanroom its own clean air supply unit, production can be continued, even if one clean air unit fails. The next level down, the airflow is transported to and fed through the individual filter elements of the cleanroom tunnels. They filter out all finally remaining dust particles larger than 1/10 of a micron. In the cleanroom, which represents but 7% of the building's total floor surface, the operations tunnels are situated on either side of a central corridor. Technology tunnels can be entered from the central corridor. Maintenance tunnels, where repair and maintenance operations are performed, can only be reached from a service corridor which completely surrounds the cleanroom. With perfect laminar flow, the clean, dust-free air continuously flows down from the ceiling of the technology tunnels and is extracted through the perforated floor. This cleanroom allows extremely clean and dust-free operations in order to produce very complex submicron ICs. A few examples of what submicron technology really means. If the complexity of a submicron IC is compared with the complex infrastructure of the City of London, the smallest IC interconnection can be compared with the narrowest alley in London. But specialists find their way out. For the production of ICs, a very clean environment is needed. So just how clean? Relatively speaking, a grain of sand in a huge cathedral would be unacceptable. Madam? Madam? Over here. Look, just here. Producing submicron ICs demands very fine accuracy and alignment. So how accurate? Try to throw a coin from an aeroplane at 25,000 feet into a teacup. Good luck. Before a silicon slice is transformed into ICs, it has to travel quite a roundabout route through numerous cleanroom processes. In the photolytic department, one of the most basic treatments is given to the slice. It is covered with a photographically sensitive layer on which IC patterns can be printed. In IC manufacture, many patterns have to be printed between different production steps. Extreme alignment accuracy and cleanliness are absolutely indispensable. The print mask is for one IC only, so it has to be printed repeatedly on the slice. In other cleanroom operations, chemical and physical reactions take place on the surface of the silicon slice. And thus, in up to 300 steps, ICs are created. The first aim in the Submicron Research and Development Center was the creation of a 1 megabit static memory, which can store 1 million bits at a time, using up to 8 million transistors on a surface of less than 1 square centimeter. But 1 megabit memories were not really the goal. They were the means to develop submicron production techniques applicable to a wide range of complicated integrated circuits. In initiating this mega project, Philips accepted an enormous challenge. While using a new factory, new equipment, new production techniques, and employing new people, the submicron technology had to be developed in one total approach. Philips succeeded. The megabit memory has actually been made. But what's more important? Theories about submicron technologies were either confirmed or altered into useful, manageable techniques. Through the startup period, it was confirmed that effective research was only possible superimposed on a continuous production process. Computer systems were introduced to verify every individual step in the process by providing information directly to the operator himself. In another application, computers are used to provide information on the progress of every silicon slice through the process. In researching submicron technology especially, it was shown that quality and reliability tests have to be performed immediately after the production process. This leads to efficient and precise research and development. Once separated from the slice and molded into plastic, the ICs are subjected to aging tests. This Philips test center, which is one of the world's most advanced IC test centers, was founded as a necessary and essential part of the IC research and development activities. Test results confirm the quality of the Eindhoven IC Research and Development Center. The results may also lead to new ideas and developments in IC design. Optimizing designs and design techniques is only one of Philips's aims. Creating new IC designs necessarily is another one. In the future, the demand for new submicron IC designs will steadily grow. Designing and producing their own integrated circuits is of vital importance to the electronics industry. Philips will not only react to the demands of the international IC market, they will meet developments to be expected and thus remain front runners